Hi everyone. Today we would be looking at the part of database. In the previous video, we have already discussed about a lot of things, including hashing, latency, and throughput. But in today's video, we would be discussing about databases, like what are the types of database, like relational databases, non-relational databases, SQL databases, NoSQL, something like that. Then we would be moving to asset transactions, why they are important. Then we will move to database indexing, strong and eventual consistency. So it is going to be a bit of long video, but believe me, you guys are going to learn a lot from it. So let's first start from the relational database. Let's start from relational. So for relational database, you can think something like that. It is based on the model introduced by E.F. Cohn. So any database that is in which the data is stored in tables, that is relations with rows and columns. Let's take an example. So let's take this as an example. We have 3 columns, and then let's say this is for name, this is roll number, and this is marks. So this particular can be called as relational. Now here strong emphasis is on data integrity and relationship is maintained, using primary and foreign keys. So what is relational database? Once again, a type of structured database in which data is stored following a tabular format, and it supports very powerful, querying using SQL. SQL. Now, what is SQL? I guess most of you must be knowing about it, but it stands for Structured Query Language. It stands for Structured Query Language. So it is used for querying and maintaining the databases, and it is typically associated with relational databases, but obviously there are a lot of exceptions. So this was it for the relational database. Now let's move to non-relational. Non-relational. Cool. So how are they different? So not based on any relational model, different types include, document, key value, columnar, and graph database. They are more flexible in terms of data storage and schema. So in contrast to the relational database, these are like free of imposed, no tabular like structure is important. So non-relational database are also referred to as NoSQL databases. So this is clear. What are relational, what are non-relational. Now let's move to SQL database. SQL databases. So when we talk about SQL, any database that supports SQL query is known as SQL database. This term is more often used with relational database, but all relational database are not SQL database. You can say one thing: all SQL are relational, all SQL maybe are relational, but all relation are vice versa, not SQL. There are exceptions. Now same happens with NoSQL. Okay, cool. Let's move to a new place. NoSQL. Now, not only SQL or non-SQL database, anything you can call it. So there is a diverse range of database technologies that is designed for big data and real-time applications, and these can be relational or non-relational, but they are NoSQL database. So you cannot use SQL here to query. So what is the definition? Any database that is not a SQL compatible is called NoSQL. That is NoSQL. So let's take an example. Take example of few. For relational, you have PostgreSQL, and then you have MySQL, you have Oracle. Cool. For okay, I will just reverse it. Yes. Let's say for non-relational. Now for non-relational, you also have a lot of examples. Let's say you have MongoDB. You have MongoDB. Then you have Redis. Then you have Neo4j. So these are some different kinds of now Neo4j is a graph based database, and Redis is a key value based. Don't worry if you guys are not able to understand these terms. Just imagine, think like this. These are non-relational. They are not like relational one. Okay, cool. I think we are done with the types of databases. So we can move to something big now. How these database works and how you want them to work. So there is a concept called acid transaction. Asset transaction. This is a concept you guys need to learn. Now, what is asset transaction? So for that, we will take a very simple example. We will take a very simple example for asset. But before that, we need to know the full form of asset. A stands for atomicity. Atomicity. Cool. C stands for consistency. I stands for isolation. Isolation. And at last, D stands for durability. Durability. Cool. So we know the full form of asset now. So we will take a very simple example to understand it. So imagine that you are at an ATM. So imagine you guys are at an ATM. I'll just name it ATM. Cool. So and you need to transfer money from your savings account to your checking account. Now, how these terms will come into play? Let's start with atomicity. We will start with atomicity. Cool. So suppose you request transfer for $100. Now the ATM must withdraw $100 from your savings and deposit $100 into your checking, from your savings to your checking. Now both operations must succeed or fail together. If there is an issue, after withdrawing like $100, so if there's a particular problem that is coming in this part, it should also arise in this part, that is in the checking part. Now the entire transaction should roll back at that process. If this fails, this should not happen. If this fails, this should not happen. It should roll back. Now ensuring that you don't lose that $100. Now the analogy here is, it's like jumping across a stream. You either make it to the other side or you don't jump at all. You either succeed or you fail, or you don't. So here, what is atomicity? The operation that constitute the transaction with either all success or all fail. You either do with 100%, you do with 100%, or 0%. This is atomicity. Now let's talk about consistency. We will talk about consistency. Same example of the bank. I will again draw it. Call it. So, like before the transaction, you had $500 in the saving. We had $500 in our saving and $200 in check-in. This is in saving and this is in check-in. $200. Now, after transferring $100, you should have this. Now you should have $400 in your saving. Now you should have $400 in your saving because you took $100 from here, and you should have $300 in check-in. So the sum before and after should remain 700. Correct? Okay. So as we were discussing, we should have $700 in total. Like here, we currently have 500 plus 200 in the beginning. The savings we have 500, and in checking we have 200. So we should have $700. Similarly, we should have after the transaction 400 in savings and 300 in checking. So at last also we should have $700. So this is known as consistency. So coming to the exact definition, after the transaction is committed or rolled back, the rules for each record will apply the same way they were applied before, and all future transactions will see the effect of the transaction that has happened right now. This is the basic concept of consistency. So we will move to the next topic now. We are done with atomicity, we are done with consistency. Cool. So let's consider this a case where we have isolation. We have isolation. So For isolation also, let's consider the same example. Let's say while you're doing one transfer at at one ATM, and your friend is checking the account balance at another ATM. So you have one ATM here, ATM 1, and then you have one ATM here, that is ATM 2. So when your friend check either the balance before your transfer was $500 in saving or $200 in check-in, and after your transfer $400 in savings and $300 in check-in, but not any intermediate inconsistency state. So it should not happen that okay, at ATM 1, when you have done that you have 400 and 300 here respectively in your savings and checking, it is still showing here that okay, 500 in savings and 200 in there. It should not, like, it is taking 1 hour to update. It is taking 1 hour to update. That should not happen, because your friend at ATM 2 will think, okay, he still hasn't done that change, so I should do in front of him. So the analogy here, think like you are reading a book and your friend borrows it and makes notes or changes. Now you had read it before the changes or after, but you wouldn't want to see the book while it's in the process of being edited, right? So the execution of multiple transactions, concurrently, will have the same effect as if they had been executed sequentially. This is the whole concept of isolation. Cool, we are done with isolation. So let's move to the last part, that is durability. We will move to durability. So coming to durability, it's also not that tough. After your transaction is successful, the transfer of your money, the ATM confirms the transaction. So if I explain this in simple words, even if the ATM or bank's computer systems crash right after that, your transfer should remain intact. When everything is back online, your transfer shouldn't be lost. Let's take an analogy for that. Suppose you are writing a diary entry, and once you have penned down an event, even if the ink spills or pages get wet later, that event remains part of your history. It doesn't get erased. Similarly, in durability, any committed transaction that has been done is written to non-volatile storage. It will not be undone by a crash, powerless storage, or any network partition. It should remain there forever. So this was the whole concept of durability. So I think we have talked about a lot of topics. So this is what ACID transactions look like. So now we can actually move to the next part, or that is database indexing. As I told you that we will be discussing about that also in this video. So let's discuss about database indexing. So let's move here. Cool. So we have database indexing. So we have database index. Cool. So let's talk about it. So we will take one more real life example to make things easy here. Just imagine that you are having a massive core book. You have a massive book now with thousands of recipes in it. If someone asks you to find a recipe for chocolate cake, how would you find it? Now, if you will say me, okay, I will give you a brute force solution, you will think you have to flip through every single page. Let's say this it has 1000 pages. It has 1000 pages. Now you will have to flip through every single page, reading each recipe title until you find the chocolate cake recipe. Now obviously this is an if I explain you why this solution comes to mind, this is a database without an index. You don't have anything that, so you will have to go through every single page or record and scan through it. Does it has a chocolate cake recipe? So this will take you a lot of time. Definitely, let's say for one page you are taking 1 minute, so you will take 1000 minutes. You will take 1000 minutes. Cool. So now with an index, what if you have an index? The power of an index. Now the book has an alphabetical index at the end. Let's say from A to Z you have. So where you can quickly look up chocolate cake and find the page number where the recipe is located. Suppose from A to Z you have at the it, and then in that you also have C. In that C there could be chocolate cake, and you have CH, then you have CHA, then you have CHB. Similarly you have CHO. Cool. So where you can quickly look up for chocolate cake and find the number of page, this would hardly take you 5 to 10 seconds. In a database with an index, instead of scanning the entire database, the entire table, the system can directly look at the index, just like the book's alphabetical index, and quickly determine where the desired record is located. So this drastically reduces the time taken to fetch a specific record. So the analogy of this whole part was using the index page in the book. Simple as that, nothing fancy. So if you want to know the exact definition of database index, a special data structure that has been created that allows your database to perform certain queries much faster. Not all obviously, but certain queries much faster. So indexes can typically only exist to reference data like stored in a relational database, obviously because you want it to be stored somewhere, something like that. Now this speeds up queries so fast. Just imagine, instead of 1000 minutes, if I am taking 2 minutes even now, that's so much less than it was taking before. So yeah, that was it for the data indexing part. So I think we are done with almost everything. So let's look at consistency at the very end. So we will look at consistency. Cool. So there are two types of consistency basically. The first is strong, and the second is eventual. Now let's look how they are different. So this strong consistency is actually usually referred when the consistency of asset transaction as opposed to the eventual, because in strong you always want the consistency of asset transaction. If that is happening, you can say that your database is strong consistency. Whereas in eventual, a consistency model which is obviously not like the strong consistency, because it was performing on asset transactions. So in this model, reads might return a view of the system that is stale. Suppose you have changed the comment section of a YouTube video from hello to hi, one of your previous comment. Now if this is not updated within next 2 minutes and a viewer come, it will still see hello and it will reply to that accordingly, but it won't be able to say okay, this has been changed to hi. So an eventual consistent database will give guarantees that the state of the database will eventually reflect writes within a time period. Let's say this can be 2 seconds, this can be 2 minutes, or this can even be 2 hours. So you have to decide which is best for your system according to your requirements. So these are the two kinds of consistency when it comes to database. So yeah, that was it from my side in this video. Talking about a lot of concepts. In the next video, we would be looking at key value stores, because we talked about that in our relational database and non-relational database. So it's very essential that you guys get to know about key value stores.